In this section, we're going to talk about something called equilibrium. Now, one thing that needs to be introduced here is something called a reversible reaction. And a reversible reaction can go both forward and backwards. So it can go in both directions. Up to this point, we've really just discussed reactions that go in the forward directions. So one thing just to point out, though, is that we always continue to call the reactants the substances on the left and the products the substance on the right. So even when we're referring to a reversible reaction, what we're still talking about reactants on the left, products on the right. The difference you'll see is that there'll be some type of arrow that indicates, like this one, a double arrow, that indicates the reaction can go both directions. You can see it here also. Now, the definition of equilibrium, you hear that word equal in it, right? It's not that the reactants and products are equal. What an equilibrium means in this instant is that the rate of the forward reaction, so how fast it's going, equals the rate of the reverse reaction. Remember, rate is how fast it's going. So when the rate of the forward reaction equals the rate of the reverse reaction, then the system is in equilibrium. And a system in equilibrium can tell us some things. So the first thing we're going to investigate is something called the equilibrium constant. The equilibrium constant is given a letter K. And you can see here in a general form, the equilibrium constant is going to compare the concentration of the products on the numerator and divide it by the concentration of the reactants in the denominator. Now this symbol, the brackets, is a short notation for concentration, or how much is present. We haven't talked about concentration units yet, but we will use them in some of our calculations. Now the equilibrium constant is determined. This is the general form of the equilibrium constant. So if I'm going to rewrite that over here so I can get it just a little bit bigger. So this is a generic equation, chemical equation, where A's, the lowercase letters, these are the coefficients from the balanced equation. And so it could even be a 1, but these lowercase letters are the numbers. And then the capital letters, these are the formulas of the substances. So these are the chemicals. So on this side we have our reactants, right? And this side we have our products, and here's our arrow in the middle. So it's just a generic chemical reaction or equation. Now K is going to equal, we want the products on the top, so that's this side. And we're going to, the equilibrium expression is simply just writing down. So you're going to take the brackets, which means concentration, and you're going to raise that to the power, whatever number is in front of substance C. And you'll multiply that, not adding, notice that it's multiplying, not adding, by the substance D, and raise that to the power of whatever the coefficient is. And if it's a 1, you won't have a number there. And then we take the reactants, which I have here as A and B, and we take the concentration of substance A, raise it to the A power, and then the concentration of substance B, and raise it to the B power. This is just a general form for the equilibrium constant, and we're going to write a few on the next pages. Now, just to point out, I am skipping this right now, but we're going to pick up these two little sections in a future slide. So let's go back to the equilibrium constant. And I've written up here are the general form. And so for here's two equations, let's write the equilibrium constant. Or it's called, I need to rephrase that. Because this right here, I keep calling it the equilibrium constant. When it's a number, this number k would be the equilibrium constant. Okay, when it's written like this, they call it an equilibrium expression. So we're not writing the equilibrium constant, we're going to write the equilibrium expression. So K equals, and we're going to put the products on top. So this is my product. So I'm going to put in brackets SO3. And then I'm going to raise it. There's a 2 in front of it. I'm going to square it. And that's all I have. On this example, I only have one product. Now I'm going to go to these reactants here. And it wouldn't matter which order. I'll just go from left to right. So I'm going to put in the brackets, which means concentration, SO2. That's the formula. And then it's raised to the second power, so I put a 2. And now I also have oxygen, not added in the equilibrium constant, multiplied. So I put oxygen, brackets mean concentration. There is no number, no coefficient, so that's a 1, so I won't put a number. And that right there is the equilibrium expression. So now let's do this for the equation, the chemical equation below. So the equilibrium expression is K equals, always put the products on top, and so I'm just going to go from left to right, although it wouldn't matter. So I'll do this one first, CH3, CH3 in brackets, that means concentration. There's no number, so that's a 1, I won't do a number. Then I'm going to multiply it by the HCl in brackets, and this has a 3, so I'll raise it to the third power. And now I'm going to do this for my reactants. It goes in the denominator, so I'll start with this one, CH4, and it doesn't matter. I just start with that left to right. There's no number, so I won't raise it to a power. And then I have Cl2, and this one has a 3, so I put it to the third. And that's the equilibrium expression for that reaction. Now, the equilibrium constant, when we have a number, tells us information. And let's take a look at that. So, an equilibrium constant, looking here, the size of the number tells us if products or reactants are favored. So when you have a reversible reaction, it doesn't mean that everything's equal. Just the forward and reverse reaction are equal, the rate. Now, sometimes before the reaction goes to into equilibrium, it produces a lot of products before it reaches equilibrium. And if a reaction produces a lot of products before it produces equilibrium, then it would favor the products. Now, on the other hand, the reaction may produce very little products and then go into equilibrium. And so really, if I could look into the container, I wouldn't see very many products. I'd see mostly reactants. And so then I would say that favors reactants. I imagine if I had some kind of magical glasses that could look into the reactants and products, when I say something favors the products, what it means is if you could look there at all the different chemicals, you'd see more products than you did reactants. Now, once it reaches equilibrium, you wouldn't really be able to tell that anything's going on because it's equal product and reactant, the rate. And so as soon as you made a product, another reactant would form because they're going back and forth and back and forth. Now, sometimes K can almost equal 1, which would mean we have both reactants and products favored. So, a reaction that favors products, back to the equilibrium constant. So, if we favor products, what we see with the equilibrium constant is it's greater than 1. An equilibrium constant, that would mean the numerator, because it has the products, is large and it's greater than 1. An equilibrium constant that favors the reactants, then, on the other hand, is going to be less than 1. So looking down at these three examples, This is a -4, so that is less than 1, so this favors the reactants. So once equilibrium is reached, there's more reactants present than there are products. It's kind of hard to believe in a reaction because I think to this point we just think there's always just products. But in an equilibrium, you have reactants and products present, because as soon as a reaction becomes reversible, you have products that are being made, but the reactants are also being made. Now K is 3 at 350. This is greater than 1, so it would favor the products. And a K here that is to the 5, that's very large, much greater than 1, and that favors the products. So you can even see that some reactions, they can favor products to different degrees. The larger the K, the more products, the smaller the K, that favors the reactants. So we can tell, in order for us to actually calculate the equilibrium constant, they have to give us the information about the concentrations. So you can see in this reaction right here, they have included numbers that I'm going to plug in. So I would start by writing the equilibrium expression, which compares the products to the reactants. Remember, the brackets mean concentration. And this time, to actually calculate the equilibrium constant, I have to have numbers that would be given for what we're doing in our class, and I'm going to plug it in. So the N2O4 is 1.26, and this capital M is for molarity. It's a concentration unit, and we don't have to really worry about it for what we're doing. And then NO2 now is 0.0760 squared. Don't forget, I often see students that write the equilibrium expression correctly, but then they don't square their results. So, let's see, 1.26. Now let's divide that by 0.0760 squared. And I get a number that's equal to 218. So looking here, this is a K that's greater than 1. So I would think that this reaction favors the products. So let's do one more problem to think about this. And before we do it, I want to review a few things because this is going to be involved in the next question. So if you remember from the previous the previous section, we had what was called the activation energy. And activation energy gives us a window or a glimpse at the reaction rate, or how fast the reaction is going. And if you recall, a higher activation energy, a faster reaction rate. And then we have delta H, which is the enthalpy change, or the other way you can think about it is the heat of reaction. And the heat of reaction will have a positive or a negative sign. And so what that's telling us is whether the products or reactants are lower in energy. So remember, if it has a positive sign, that is endothermic, and the reactants are lower in energy. If it has a negative sign, it's exothermic, and the products are lower in energy. And now we've added something called K. And remember, K is our equilibrium constant. And the value of K determines if the products or reactants are favored. So remember, a K that is greater than 1, that favors products. A K less than 1 favors reactants. And a K that's right around 1 has both. So now we have 3 values that help us understand a little bit about the energy in chemical reactions and how fast they're going. Now, down here, you can see that there's some things that are very favored. So the products, if we're making more products of a reaction, are favored when K is very large, greater than 1, and when delta H is negative, or an exothermic reaction. So those two things together are very favored in a chemical reaction. That would tell us if K is much greater than 1 and if you have an exothermic reaction. So here's a reaction. And let's think about what we know about activation energy, the delta H, the heat of the reaction, and the equilibrium constant. So there's a reaction, and it tells us that K is 1.1 times 10 to the 10 to the 7. So the first part says write the equilibrium expression. Well, let's practice that. We take our products, which is this here, so it's H2S, and then remember squared because it has a 2 right here. And then that's over the reactants, which are here. So that is H2, and that's going to be squared because of the 2, times S2 with no number because there's no number here. So that answers the first question. The second one says, are products or reactants favored? Well, that's where this value of K comes in. So K is much greater than 1, so we know that the products are favored. Now, it's the letter C says, would you predict delta H, the energy of the reaction, to be positive or negative? Well, I know with a very large K, that means the reaction is favored. So I would predict that it is negative because I know a K that's much larger than 1 would go along with an exothermic or with a delta H that is negative. Now, are reactants or products lower in energy? In exothermic, energy is released, so that means the products have lower energy because energy is released and it loses energy from the reactants. And then letter E, would you predict this reaction to be fast or slow? This is kind of a trick question. We can't determine from delta H or from K if it's a fast or slow reaction. What determines if a reaction is fast or slow? Well, from what we've been learning so far, it's the activation energy. And so if we don't know the activation energy, then it's hard for us to predict if it's fast or slow. Because a favored reaction, one that has a large K and a negative delta H, may still be a slow reaction.